Hello everybody. So this is our first YouTube live session. So we are making these videos on the channel Maths for All for quite some time now, and we are getting feedback from some students and some members that we should start with these live sessions. So the idea is that for now the idea is that already have the lecture series on linear algebra. So here we will be having a summary of the linear algebra things, and then we will discuss some questions. So main focus will be on the previous year's exams where linear algebra is a part. For example, we have UGC CSIR, we have NBHM exam, we have GATE exam, and we have IAS exam where linear algebra is a part, and in fact a substantial part for the exam syllabus. So we will try to keep the session as much as interactive as possible. So I would encourage all of you to ask questions, right? So I'm still waiting for people to join so that we can start. I think we can wait for 5 minutes, and whosoever join, you can send a message right now. If you have anything, you can just chat. You can write in chat your name or what you want. You have any suggestions, you can put it in the chat box. So I'll wait for 2-3 more minutes, then I'll start with the linear algebra part. So for today's we will be starting with vector spaces and vector subspaces. That is the idea, and discussing some questions. So we'll wait for 2-3 more minutes and then we'll start. Thank you. So let us start. So this is I'll call it as summary video. So this video will be helpful when you are going to have your exam tomorrow, right? So you have very less time left with you, and you want to just quickly go through all the syllabus. At that time you have to at that time you can go for these videos. So let us see what is the summary for today. So we are going to discuss vector spaces. Yeah. So here is Abhinandan. He is saying, good afternoon. We welcome you, Abhinandan. Thank you so much for joining. And we hope that you will learn from this video, and you can give your suggestions in the chat box for the improvements. So if there is any problem, because this is the first time we are going live, so there may be some technical glitches, right? You can just let us know. So we'll start with this vector space. So most of us, we know what is a vector space. So but for the sake of completeness, let us write down what is a vector space. So we have here, suppose you have a non-zero set. So you have a non-zero set V, non-zero set V, and then you have a field. Okay, so some of you may not know what is a field. So we can make the thing simple, and we can just you can think of right now it as a space of all real numbers or a space of all complex numbers. You just keep in your mind that this is what we are taking as of now. Then what we have two operations. One is from V cross V to V, that is called a binary operation on V, binary operation on B, and the another one is from F cross V to V, right? So this we will denote with a dot. So this is called a scalar multiplication operator, scalar multiplication. So the idea is a vector space is not just a set. It is a set plus two operations. So generally you will see that in some books they denote vector space like this, right? So you have a vector space and two operations, right? And these operations should satisfy some conditions, and there are total 10 conditions. So let me write down those conditions. So first is, if you denote U and V, these are from your set V, then U star V should be in V. Although this property is itself there, because we are saying that star is a map from V cross V to V. So this is the first property. Second property says that you should have additive identity. You should have additive identity. So now, what is additive identity? So additive identity is for each u belonging to your set V, there should be an element E, right? Such that u star E is equal to u is equal to E star u, and this particular element, which is your identity element, it should be unique. It should be a unique element of your space. So you should have in your vector space, in your set, there should be a unique element E such that this thing is satisfied. And then the third property is for each U in your set V, you should have minus U. So minus u does not mean that it is negative of u. It is just another element of V, such that u plus u star minus u should be equal to your additive identity. This should be equal to minus u star u. I'll give you example and that will make the things more clear. Right. And then the fourth property is that you should have associativity law, that is u star v star w should be equal to u star v star w, and then you should have commutative property, that is u star v should be equal to v star w, right? So these are the 5 properties which the star operation should satisfy. And then now let us come to the multiplication operator, scalar multiplication operator, which is from f cross v to v, right? So the first property is simple. If you choose alpha from f and v from your set, then alpha dot v should be in v for all alpha in your field f and v in your vector space v, right? And then we have these properties that alpha u star v should be alpha dot u star alpha dot v. Then you should have alpha plus beta. Now this plus operation is from your field, right? Dot with u should be alpha dot u plus beta dot u. Here, because we are in the vector space, so this plus operator is actually your star operator, right? And then you should have alpha beta. Now in the field you can define the multiplication of two elements. So you have alpha beta, this is the multiplication in the field. Star dot with u should be alpha dot beta dot u. And then you should have, because there is identity element in the field, we already know this thing, so we should have that 1 dot u, just a minute, 1 dot u should be equal to u for all u in your vector space V. Here 1 is the identity element of the field. Fine. Now I will give you examples. So first example and the simplest example I am giving you is the space of all polynomials of degree less than is equal to n. So let us look at the example. Space of all polynomials of degree less than equal to n. Polynomials of degree less than is equal to n, and I am taking the coefficients from real. Coefficients are real. So we denote this space with p and x, where x is the variable you are talking about in which you are making your polynomials, and we claim that p and x forms a vector space over the field of reals. Right. So let us see this thing. So p and x is actually a naught plus a1x plus a2x square plus so on an x raised to power n, where ai's are real. Right. Now if you are saying that something is a vector space, then you should define the star operation and the scalar multiplication operator. So we define here star operation simply that if you have two polynomials, say p1x, say p1x is a naught plus a1x plus a2x square plus so on an x raised to power n, and another polynomial which is p2x, say that is your b naught plus b1x plus b2x square and so on bn x raised to power n. So you can define the star operation, which is actually here star operation. I'll write this thing as simple addition because we are just adding two polynomials and we know how to add two polynomials component wise. So this is a naught plus b naught plus a1 plus b1x plus a2 plus b2 x square and so on. You have at the end an plus bn x raised to power n. So this is how you are defining your addition operator or your star operator, and then you can define the dot operation, scalar multiplication operation as, right, so you have this dot operation as alpha into a naught plus a1x plus a2x square plus so on an x raised to power n. So you can do, this is from real, this alpha is a real number, right, and this a naught is real, so this is alpha a naught, this is a real number, plus then you have alpha a1x plus alpha a2x square and so on alpha an x raised to power n. So this is how you are defining your star operation, which is a binary operation on V, and this is the scalar multiplication operation. Now you can verify all the 10 properties. So clearly if you add two elements u plus v is in V is your Pn here. We know that if you add two polynomials of degree less than is equal to n, then you will get a polynomial of degree less than is equal to n. So this property is true. First property is true. Now second property, you are looking for an element such that if you add that element to all your elements, you should get the same element back. So here we have 0. 0 is a polynomial of degree less than is equal to n. So we have u plus 0 is equal to u is equal to 0 plus u for all u in your Pn. For all the polynomials you take, if you add the 0 polynomial to your polynomial, you will get your polynomial back, right? So this is your additive identity. Now the third property, that for each polynomial u, say you have a polynomial a naught plus a1x plus so on an x raised to power n. Now you are looking for a polynomial, so that if you add that polynomial in your polynomial, you should get the additive identity, which is 0 here. So you know that if a naught is a real number, then minus a naught is also a real number. So you have minus a naught. If a1 is a real number, then minus a1 is also a real number, right, and so on. So you have minus an x raised to power n. So given this u, you can define this minus u, right, and if you add this minus u to your u, you will get 0 polynomial. So it means that there is identity additive inverse for each element in your vector space, in your set, which we are claiming is a vector space, right. So third property is also true. And also the fourth and fifth property, they are easy because you know that addition of polynomials is associative and it is also commutative, right. So next property, that is u plus v plus w is equal to u plus v plus w. It comes from the associativity property of real numbers, and also u plus v is equal to v plus u, that is from the commutative property of real numbers, right. Now let us look at the other properties that are very easy to establish. Let us look at the property of scalar multiplication. If you have a scalar alpha and you are multiplying it with a polynomial a1x and so on, so that is an x raised to power n, then alpha is a real number, a naught is a real number, so you will get alpha a naught is a real number. So this is again a polynomial of degree less than is equal to n with real coefficients, right. Then next property, if you want to look at, that is also easy to verify. So you have alpha plus beta dot with a polynomial. Obviously you'll get alpha dot u plus beta dot u, and then you have alpha u plus v, where u and v are polynomials, that is also equal to alpha u plus beta u, right, beta v, sorry. And then you have next property, that is alpha into beta, this is the multiplication of two real numbers, dot with u will be equal to alpha dot beta dot u. And also the last property, we know that 1 is an element of real numbers, and if you multiply it with the polynomial u, that is each coefficient you are multiplying with 1, you will get your polynomial back. So all the 10 properties are there. Therefore this Pn X is a with a vector space, is a vector space. Right. So I just gave you an example of a vector space. Now I want you to create an example of a set which is not a vector space. So just think of, I am giving you 2 minutes. Let me write down what I am asking. I already told you that what is P and X. I told you this is a vector space. So I am asking you to modify this Pn little bit, very little modification you have to do. Modify it so that the final set you create, is not a vector space. Final set you create is not a vector space. Do it and just type in the chat box, please. Right. So again I'll repeat that I gave you P and X, which is the vector space. I want you to think about a change in the little bit change in this P and X set so that you get something which is not a vector space. Okay, so let me tell you what that is. So you see, P and X I defined as set of all polynomials of degree less than is equal to n. Now you modify it. Define a set all polynomials of degree exactly n. All polynomials of degree exactly n. Right. So you have a set where you are saying it is a0 plus a1x plus a2x square and so on an x raised to power n, and you are saying that an should not be 0 because of this exactly word. Okay. And this ai's, all other ai's are 0, sorry, are real. All other ai's are real. Now you see, if I take two elements from this set, you take this element, say your element is a0 a0 plus a1x plus so on. So suppose this is 5x raised to power n. Another element, if I choose something like b0 plus b1x and so on, and here instead of 5 I am choosing minus 5x raised to power n. If you add these two elements u plus v, what you will get? You will get a polynomial of degree less than n because these elements will cancel. So it does not belong to the set, the nude set, you call it say P, does not belong to P. So we don't have the binary operation on P. Therefore, it is not a vector space. P with the addition and multiplication which we have defined above is not a vector space, is not a vector space.